Yeah, that's probably a good answer. You know, most of the people that say they know about neural nets don't know about neural nets. So, okay. Well, we'll get started. And so we're going to talk about Verum, but I expect really that I think you're probably going to be disappointed in this presentation for one of three reasons, right? But I'm the first talk, so I can set the bar low, and everyone else can build from there. And so, you know, you may see this, and you may just think, you know, this is just another threat feed thing, right? You know, it's practical, but in reality, there's all these new threat feed things. They're all innovative, and everyone's saying, no, threat feeds are dead. But take ours, it's not. You know, our thing is really good. Or you may just think, you know, there's all sorts of cool machine learning and stuff, but maybe this is all theoretical and there's really no practical part to it, right? Because everyone likes to put machine learning into their presentation. And in reality, you know, how much of that do you actually see come out and turn into anything useful? You know, for the actual machine learning people in here, you're going to be disappointed because I'm not going to have any cool validation data. I'm not going to have a confusion matrix that says that, you know, my true positive rate is 98.37 whatever %. Right? And this is okay. Because you know, what I want is that, you know, I want you to come back and think about this later. So, you know, a few hours or days or weeks or months or something, come back and think about what I'm going to show you. Because I'm going to show you something really cool. I'm going to show you a machine thinking. And in the literalist term. And I looked it up in a dictionary. Well, I didn't look it up in a dictionary. No one does that. I looked it up on Google. But the definition for thinking is direct one's mind towards someone or something. Use one's mind actively to form connected ideas. And that's what we're going to do here. That's what I'm going to demonstrate, is a machine doing that. And we're going to try to do a demo where we're going to give the machine just something easy, right? An IP address, but it's something it's never seen before. And it's going to form a thought about that IP based on what it knows. And so let's go into the kind of the obligatory agenda side. The only thing, like, I bring up the DBIR thing because I'm going to talk about DBIR data here, and so that's more for full disclosure than anything else. All the really interesting stuff is on the right. And so we're going to start with what the problem is, because who here is defense? Who here is blue team? Good, because I like blue team. Who here is red team? Good for you. We're going to talk about defense and what the defensive problem really is. And then we'll talk about why maybe threat intel really isn't solving that problem. And I assume, I don't know, I don't see Dia in the room, so maybe I don't have any like PhD graph theory people in here. So we'll cover some of the graph theory stuff, and you'll need that to kind of to figure out Verum, which is really what we're going to talk about. So understanding the problem. Anyone know what this is? This is the 2015 DBIR, visualized as an attack graph. Attacks start at this little blue dot down here. They move up into the red dots, which are the actions that attackers take. They move into the green dots, which are the attributes that the attackers compromise, and then they go to the purple dot, which is the end, right? And this is based off of Verum, which it's on GitHub. It's just the structure, the schema we use for storing breach data. And so this is made up of two things, right? Events, which are the actions attacker takes, as well as conditions, kind of the states that they put us in when they compromise things, when they compromise attributes. And so our job is to make it as hard as possible for the attacker to go from that starting dot up to that ending dot. That is our job on defense, right? To make it as hard as possible, or expensive, or long to do. Because attackers, when we do that, we do one of three things. One, most attacks are opportunistic. The DBR data says that. And so if you become hard, they go after someone else. Or if they're just really crappy hackers, you just price them out of the market. They can't attack you anymore because it's too expensive, it's too hard. And even if they're the good guys, the good attackers that have the skills and capabilities, because they're spending more, they can do less, right? They can do this attack, but maybe they can't do the next. And so we do this in two ways. We make the paths, we take the shortest paths, and we try to get rid of them, right? We want to try to get rid of the easiest, the shortest way to get from here to there. And when we can't get rid of it, what we do is we try to make it longer and make it harder. And so for any single path, or any single attack, it's a path through the graph. This is like your standard attack, right? It starts with a phishing attack where they get someone to go to a malicious website which downloads data, and then that's used to go compromise the host and to hack into it to steal secrets. And it's this path through the graph. And these paths can be long, they can be short, they can go back and forth, right? back and forth between actions and attributes and back and forth, or one breach can lead to the next, and the next breach leads to the next. They kind of cycle. It's not really a line. It's more of a geometric thing back and forth. And so when we talk about a single situation, our job as defenders is twofold. First, our defense has to be quicker than their attack path. And second, the magnitude of our defense has to be bigger than the magnitude of their attack. So what we're saying here is that when they take the field, we have to take the field before they've won the game and left. And that doesn't always happen. In fact, normally what happens in security is they take the field, they play the game, they leave, and then we come afterwards and go, damn it, we lost. But even if we get on the field while they're still playing, our game has to be stronger than their game. And of course, the problem here, right, is they get to pick when the game starts. The benefit, though, is we own the field. And so we're going to be talking about the T to detect, right, because defense is a couple of things. First we have to figure out that they're there and they're playing. Then we have to go tell our other teammates, hey, we got to go get on the field. Then you actually have to decide to get on the field, and you have to get on the field. And we're going to talk about specifically detecting the attacker, finding out that the game started, because that's what Verum does. And so, against my better judgment, I put a video slide in here. But it's Meredith from last year, and she did a really great talk on LangSec. And so I wanted to play a video from her talk. Sorry, I leaned back and forth against the mic. It just kills the sound. So let me get this playing here. Yo. Defense does. Let me turn this up. Oh, the audio thing is on the floor now. So. Yeah. Nah. Don't worry about it. So we'll just play through this video. And what she's saying is that an attack starts when an unknown agent acts, right? A person you don't know does something. And they do a couple of things, right?
Interactions that have happened in the past, both with you and with other entities. You know, here the quality of your data is really important. You know, if you're getting fed noisy information about how an agent has interacted with other agents in the past, the extent to which that can help you is limited, although there are probabilistic methods that can make that a little better.
So, you know, what she said there is that the unknown agent acts, and there's signal that they communicate directly to you. But there's also kind of this side effect information that they pass you, and you've got the historic information on. And so our job then is how do we react? And of course we react based on what we know, which leads us to go and say, what do we know? So this is the Lockheed Martin cyber kill chain. And we talked about before, attacks really aren't quite linear. They're more geometric. They cycle and stuff. But this is a good kind of post to hang our hat on as we talk about things. You know, we look at recon. So maybe they scan us. Maybe they scan something else, or they kind of do it indirectly. They could be interacting with us here. We could be getting data. During weaponization, they're probably not interacting with us. So if you go and read like the Finfisher attack, right, he went and he figured out what software was running on his target, and then he went to a bunch of companies that were running that software. So there was no direct signal, but there were side effects that would you would potentially be able to pick up. And then when they're doing delivery, exploit, installation, C2, actions on objectives, those are all things that are directly interactive with us, right? The attacker is communicating directly with us when they do those things. So this is our opportunity to do something. But the attackers aren't stupid, right? They know they're communicating to us. And so they're going to give us the signal that is the least useful. And so this leads us to David Bianco's pyramid of pain, right? This is the stuff the attacker gives us. Domain names, IP addresses, hash values, all those things which are very easy for them to change. And so our job is to try to figure out and get this information, you know, the artifacts, the tools, the TTPs, you know, and what about going beyond that? The infrastructure that the attackers work on, the OpenDNS guys, this is DIA, and the OpenDNS guys talked about this last year at Black Hat and such. What the infrastructure that's behind the attack, not the upfront stuff, but the servers and stuff, those don't change as much as the IPs, the domains, the front stuff that we get. And what about personas, right? So behind all these attacks, there is someone. Hopefully there's someone. Otherwise, the computers are getting way too smart. There's someone. And if we can find that persona, that's something that's hard to change, right? Because there's the Dread Pirate Roberts. And the Dread Pirate Roberts had email addresses. He's got accounts. He's got personal IPs. He's got browser signatures, handles, names. In fact, there's a Dread Pirate Roberts, and then there's his persona that he goes home and hugs his mother with. And that's his real persona. That's really hard to change. In fact, these guys get caught because you can trace back from their malicious persona to their real persona. They made some link back in time, whether it's Dread Pirate Roberts or Sabu. That's how they got caught. And so there's opportunity here, right? There's that communicated information, which changes a lot. It's not really as useful up front. But if we can find our way back through the infrastructure, through the TTPs, to the personas, there's potential. But there's a lot of challenge in that. And so our job in that T to detect is detecting the communicated signal quickly. That's what we have to do. And that leads us to why threat intelligence isn't doing this. And I'm not the first person to talk about this. This is Alex Pinto, a really smart guy. Don't ever ask him how smart he is because he's way too humble. But he is incredibly smart and has done really cool machine learning stuff for information security. Last year, he was up here in the same spot talking about information security and threat intelligence feeds and talking about how they aren't particularly useful. And he built a tool, TIQ test, which lets you go and run some stats on, as well as Combine, which lets you go and enrich and kind of get a consistent answer for these. But we used some of his data in the 2015 DBIR, and we found, and our data agreed with it as well. We did some similar testing over the summer. And so we found that there's this 3% overlap, and most of it happens in this inbound section. So 3% overlap in your threat intelligence feeds, right? That means that 97% are unique. Unique IPs, unique domains, unique encoded malware. It's actually all the same malware. It's like 20 families, but it looks unique from a hash standpoint. And so what's happening here is that if it doesn't come back in your feed, it's not useful to you. So picture this, right? Something happens, and that generates a threat hit on your threat intelligence feed. And so in theory, what should happen is something else should happen, because that's where you catch it, because what's in your threat. But in reality, something else happens, and when that happens, that should have hit another hit in your threat intelligence feed, that's that overlap, right? That's not happening. And what that means is that the past isn't predicting the future. If that's not the case, your threat intelligence feed is not predicting what's going to go happen. And maybe you're thinking, I can catch it while it's still happening. And the reality is that's unlikely. The data shows that the attack lasts a day, and in reality, the resolution of our data was like a day. It's more like 4 hours, right? And they're only hitting one person with those indicators. So you're not even going to catch it during the attack unless you can act extremely quickly within your own company. But, what if we weren't just working with what the feed had in it? What if we could go and trace back, take what was communicated, work our way back to the TTPs, the infrastructure, the things that don't change? What if we could establish a context around what was communicated? Then the next time an unknown agent acts, we'd have the opportunity to put what they did, or what they communicated, into context, and we'd be able to figure out who they were and what they were doing. And so that's what Verum does. And this is a graph. This is some of the Verum stuff I did last year. But before we get into it, we need to talk a little graph theory. And by the way, are there any graph theory people in the room, really, the master's, PhD people? Good, because I'm just self-trained. I probably have big portions of the knowledge base missing, and it's a very academic field. And so if I make any huge mistakes, feel free to correct me, preferably after the talk when I'm not on the clock. We're going to hit right around 45 minutes for this. So for graph theory, there's two things you need to know. This is why I love it. It's so simple. The first thing you need to know is that you can only have two things in your graph: nodes and edges. No more, no less. The second rule is that every end of a node, or every end of an edge, needs to be connected to a node. And so if you have a line that's an edge, you need to have a node at each end. In fact, you can have a node and just have both ends of the edge connected to the same node, right? Or you can have a edge that has lots of endpoints, and you can put just a bunch of nodes on them. But you have to have a node on every end. Now, this is NetFlow, right? This is each node is a host. The edges are the flows. You can see all the data on it. Those are all properties of the flow. And this is also NetFlow. Except here, each node is an atomic piece of data, and the edges are the relationships between the data. But because both of these have properties on the nodes and edges, this is a property graph. And really, all the graphs you deal with are going to be property graphs where they've got this kind of data on them. In fact, these aren't just property graphs. They're directed, right? Because a flow has a source and a destination. It goes to something. So it's not really a line. It's a arrow between two things. And so that's a property graph. And this is really the same way. Things go from the flow ID to the piece of information. And in fact, these are also multigraphs, where a multigraph is when you have two nodes. And of course, you're not just going to have one flow between them. You're going to have multiple. And so in a multigraph, you have multiple edges between the same two nodes. And really, the important thing here is it affects the underlying structure in whatever you're using to store the graph. And so you kind of have to figure that out up front. It's not something that once you've got it kind of your graph started and building, it's not a big deal. But you have to understand it for the structure, for the storage infrastructure underneath what you're doing. And so those are kinds of the types of graphs, or some of them. And really, a graph can be multiple of them, obviously. And so we see a lot of graphs. We see structures for graphs just in how they kind of arise, right? Because there's what are called acyclic graphs, where node A goes to node B and node C. And they both go to node D, but you can't ever make it back to A. There's no path back. And in fact, trees, right, which we all use from networking, right, you can only have one parent for every node. So node A goes to node B and C. Node B can go to D and E, and C can go to F and G, but they can't ever come back together. And there's a whole bunch of structures for graphs, and they all have their own properties. And so when people think graphs, I think they think this. Something like this, right? You think graph, when you think looking at a graph, you should think this. This is what graphs really look like in the real world when you get real data in them and they start to fill them up. Graphs are ugly, and they're completely useless to look at. Like, you can't tell anything from this thing. It's a huge ball of yarn. And this is really the thing, is people think that graphs are something you look at. They're useful to look at, and they can look pretty, right? You can make pretty looking ones, but once you get above 150,000 nodes, or if it's a really dense graph, it's just not going to look right. But the power of graphs is not in how they look, it's in the algorithms you run on them. And the most basic algorithms are the searches. So a breadth first search, there's two real types. A breadth first search is like taking a rock and tossing it into the river. Right? The search starts where it hits, and then it comes out 1, and then it comes out 2, and then 3, and it searches out from the node you're searching from. And if that's kind of tossing in the river, then a depth first search is like skipping the rock, right? Because it goes all the way out, and then it searches everything out there, and then it steps back, and then it searches, goes out again, searches, and it just works its way back to the node that you search from. But what I really like to use is what's called a random walk. A random walk, or a drunken walk, that's a fun name for it, is you start at a node and you do something there, like you leave a counter, and then you just kind of randomly choose a child node and you step there and you leave a counter there, and then you randomly choose another one, and you keep walking around your graph doing that. And the cool thing is you just kind of make your way around, and every once in a while you're going to come to a node that has no children, so from there you're just going to jump back somewhere. And in fact, maybe you just want to jump randomly just because, say 5% of the time. And that's a very useful thing to do, because that leads to things like centrality, like specifically eigenvector centrality, which eigenvector centrality, PageRank is a form of eigenvector centrality. So this is what made Google all that money. This is why Google is big, because of graphs and random walks. But centrality can be done in multiple ways. If you want, go to the Wikipedia page, and there's a great visualization of multiple types of centrality and how they change depending on how you calculate it. Now, another common thing to do from a data science perspective is clustering. And so starting out with clustering, there's what are called components in graphs. This one has this big, giant component in the middle. But you can see these little dots out here. Those are nodes that have no connection back to the giant component. And there could be 2 or 3 nodes here kind of interconnected. That's its own component. And if components are the portions of the graph that are completely disconnected, clicks are the portion of the graph that are completely connected. And so if I've got a click of 4 nodes, one of the nodes is connected to the other 3. And in fact, each of the nodes is connected to the other 3. And so that's a click. And that's really connected. But both of those are kind of the extremes. You want something in the middle, and that's called modularity. Modularity generally says this portion of the graph is just more connected to itself than the other. So it would say that, hey, this portion of the graph is more connected to itself than this portion of the graph. So you got a modularity cluster up here and one down here. And those are important. We'll explain why later. And you got a bunch of other things you can do, right? You can do path transversal and path searching. You can do link salience. Who here has run any kind of machine learning algorithm? Oh, cool. Perfect. So graphs appear a ton in machine learning algorithms. Your perceptron nets, your neural nets, your Bayesian networks, your decision trees, Markov chains, Markov processes, those are all directed graphs. Is anyone running recumbent neural nets? Oh, good. Okay, so all of those, everything but recumbent neural nets are also acyclic. You can't go back. But undirected graphs also get a lot of use in machine learning. So a hierarchical clustering, dbScan, k-means, k-nearest neighbors, and all of those you're forming a graph because you're taking each node and you're finding out what its distance is from every other node. And you're making your calculations on those distances. So graphs are incredibly important for machine learning. And if you've never worked, and if you take nothing else away from the graph portion of this, what I want you to remember is that graphs are about the relationships, whether it's in neural nets or decision trees or any type of graph. It's about how is this piece of data related to this piece of data. Now, if you've got a million rows, a million observations of data, or your observations are 40 features long, use a data frame for it. Use a data table. Those are good for tables. But if you want to know how this piece of data is related to this piece of data, it's what you use a graph for. And that's what Verum does, right? And that's what our context that we're talking about does. And so we'll get into it. So going back to our goal here, right? Our goal was to make that T to detect, take that signal, and to detect it as quickly as possible. But the problem, of course, was that pyramid of pain where all the things we get are at the bottom of it. And we want the stuff at the top. And so our solution was to establish a context, connect those things at the bottom up to the things at the top and beyond. And that's what Verum does, is it builds and queries that context using a context graph, which is exactly what it sounds like, right? It's just a graph that has a bunch of data put into context. The cool thing is it doesn't matter what that data is, right? It can be anything. And so to understand it, we need to understand the schema that underlies it. The same way databases have a schema that defines them, graphs can have a schema that explains what kinds of nodes connect to what other kinds of nodes. And the important part here are the key value pairs, right? If we go back and look at that, the graphs we had before, especially that NetFlow graph, right? We had like an IP, and then we had the IP past it. We had domain, and we had domain past it. We had these key value pairs, but we could put anything we want into those key value pairs. It doesn't have to be the obvious stuff. It could be IP and domain, or it could be email and value, or it could be address and something. It could be time of day that the person works and the time of day that they start working. It could be classifications. It could be classification and malice. It could be malware and the type of malware, or malware family and the family. You can put any kind of data you want into this, and it can connect it. And that's what the relationships do. They explain which pieces of data describe which other pieces of data. And that gives us our context graph. And we're mainly talking about attributes here. We talked about the context graph, and that's attributes. We talked about the attack graph. That's the events and conditions. And the actors help us link the context to the attack graph. But we'll save attack graphs and all that stuff for another day. That's next talk. So when you do it, it looks like this. This is useful, right? No, we already covered this. This is horribly useless. It looks something, but you can't figure anything out from this. You can kind of see there's stuff clustered here in the middle, and there's stuff around the edge, but you couldn't act on this without using an algorithm. What's here is this is a set of enriched data from a threat intelligence feed of C2 domains, enriched and all connected back together. And that's, in fact, what the demonstration we'll use is built on, a much bigger version of this. You can see a couple clusters. There might be something there. But before we do that, we need to understand the implementation for Verum. So Verum really, at its core, is a plugin manager. Because a lot of the things you want to do, you want to be able to add to and subtract from. And so really what you need is not one thing to do it all, but the ability to glue it all together. And so it starts out with the enrichment plugins. And enrichments are the way you build context around data. It could be that translating a domain into an IP or an IP into a country. And that's fun, but everyone does that. But what if it was like a neural net where you put in a domain, and on the other side, you got out whether that domain was a DGA-generated domain or not? Or even better yet, what if you put in an email address, and what you got out was a Google search of that address run through LDA analysis and all the relevant topics identified. Right? You can make that enrichment as smart or as dumb or as simple as you want. And you can build as many of them as you want. You know, it's a plug-in manager. You can just add them in. But once you've built that context, it's got to go somewhere. And so that's where the interface plugins come in. And I built a couple. NetworkX, so this is all built in Python, obviously, because it's on the slide. NetworkX is a graph module for Python. And so this is like if you want to just do something for the week. You really don't care if it sticks around. It works good. It's in memory. But it's not going to get big. It's not going to be particularly persistent. Who here is familiar with Neo4j? Anyone? Yeah. It's a good graph database when you want to deal with, not a huge amount of stuff, but a little bit, a couple million nodes. It runs on a single host. It's really easy to get set up. And so that's kind of your next step up. And then if you need the big, laterally distributed architecture, then you got to use TitanDB, which is, it runs on Elasticsearch and Cassandra and a bunch of other things. It's kind of a bear to work with, but it can scale. You can have 100 nodes storing your graph. But then you've got that context, and that's not really, it's nice, but you got to be able to actually think about that context. And that's what the scoring algorithm is doing. We'll talk about that later. But what I like are the minions. Who here is in ops, defensive ops? Okay, so tell me if this is something you heard. Like, you come to this system, and it's like, hey, here are your high alerts. And so you, like, okay, I'll investigate that one. And so you take that, and then the first thing you do is a bunch of stuff the computer should have done already. You go Google it. You go and put it into the search engine and collect this piece of data about it. You go and search for it in the SIM. You go and you build up all this context, but you're doing it manually. You're doing all these things that computers should have done for you, for it. What you need is like the little minions from Despicable Me running around and doing all this tedious menial stuff for you. And they need to be collecting it so that when you show up, you say, oh, I want to know about this. And it goes, great, I've already collected all the stuff you need to know. And that's what minions do. They get their own copy of Verum, and they can run all the enrichments they want. They can be pulling in threat intelligence feeds. They can be pulling in things like Alexa top million for, benign. I know it's not really benign, but, it's hard to get benign classification. In fact, if all the ops people would, every time you do an incident, you go, this is a false positive, send that to me. I can use that to go classify things as benign. That's a source of data that we're not using. But you can build your minions to do that. They can go and clean up the graph. They can go and find duplicate pieces of data or combine things that really should be together. They can go and say, hey, this thing hasn't been enriched or it hasn't been enriched in a while. Let's add more data to it. And so they do all the hard work for you. And so now it's time to start talking about what Verum actually does. So you have to start by teaching it. It can't think if it doesn't know anything. And so to do this, we run those enrichments. Right? We run the minions, we run the enrichments, and we collect data, and we continuously put it into the graph. And what we're doing is we're teaching, it's like teaching a 5-year-old, right? You're putting stuff into its brain that you can use later. And so you're adding this information. It's not particularly easy, too, because you have to make sure that that data gets in and gets merged correctly with the underlying graph structure. It means you have to make sure that this node actually ends up connected to this node. They need to be the same node when you put them in. And even worse is you have to get the relationship to carry over. Because if it's connected to nodes A and B over here, those nodes aren't named A and B over on the context graph. So you need to make the transition. But the plugins that are there do that for you, which is the nice thing. However, if anyone's going to go write a plugin for anything else, it's not fun, trust me. I'm not supposed to step on those cables. So now when we put relationships in, we actually let duplicates get in there. We're not going to try to deduplicate the edges, even though we deduplicate the nodes. And the reason is twofold. One, we have to deduplicate the nodes. But the edges, we don't have to, and it's really slow to do. Two, a lot of times the edges are coming from different places. So if you have multiple edges that tell you, hey, this is related to this, you want to capture that stronger bond between them. Now, this is also kind of garbage in, garbage out. It can take a little bit of bad data, but if you feed it all bad stuff, right? If you teach your 5-year-old all complete BS, that is all it will know is complete BS. This is the same way. It needs to understand good data, otherwise it's not going to make good decisions. But let's say you've taught it, and it's got all this information built up in its mind. Now it's time to start thinking. But when we talked about starting thinking, right, you start with a topic. You start with something that you're thinking about. Maybe that's an IP address or a domain. Maybe it's an email address. Maybe it's a collection of IP addresses. You want to know, are these all similar? Are they different? And so you take that topic, and you have to go form a memory around it. And for us, a memory means a subgraph within the context graph. And what we do is we go into the subgraph, or go into the context graph, and we say, okay, here's my topic. Go and get everything within X number of nodes, which sounds easy until these are what are called small world graphs. What it means is that you get 5 or 6 nodes out, and you have touched half the graph. But you've got a couple million nodes. That is a big subgraph. And so we're going to do a little bit of optimization. When we hit a high degree node, we're not going to go past it because it's unlikely that hitting that high degree node is going to give us better context past. And there's some types of nodes that we're just going to filter out because we know they're kind of aggregators. They collect connections in, and they're not going to add to our knowledge. And if we do that, we can get a reasonable context back out. And so we get this memory now. We've got the subgraph that forms the memory. And now we need to do the thinking part about it, right? In our definition of thinking, it was form a memory around a topic and then think about the interconnected pieces of that thought. And this is what Verum can do. And in fact, it can do it in a couple ways. It can figure out, hey, if I put in a bunch of IPs, which IPs are similar to which other IPs, right? That's clustering. It can say, you can ask it questions like, is this good? Is this bad? Is this malicious? Is this benign? Is this C2? Is this not C2? And it can do that classification. It can do it with confidence. And one thing it can do that most other things can't is it can provide you the context that you answer that in, right? If you ask a neural net, is this a picture of a baboon? It can answer, is this a picture of a baboon? If you ask it, why is this a picture of a baboon? It goes, it doesn't know, right? You can't figure out what the intermediate features are. Like, we just don't know how neural nets work on the inside very well. This, on the other hand, you can go figure out why it thought it was a baboon. You can go and pick apart internal pieces to figure that out. Now, when we do clustering, like we said, there's a couple ways you can do it. You can do component clustering or click identification, but really you're probably going to run a scoring plugin that does modularity on that subgraph. And that'll divide up this piece from that piece and figure out what's what. But the fun stuff comes in the classification. And I managed to fail a couple times at this before I got anything that worked at all. So the first failure was using PageRank. So I just ran PageRank against the graph. And it figured out which things were important, but they weren't the things that were important to the topic. So that didn't work. So then I went and tried just a linear scoring. How far are these nodes from the topic nodes? And I mean, it happened really quick. It worked really quick. And the scores were absolute crap. Because even though it couldn't take into account that even though this thing was a couple of hops out, there were tons of connections over to it. And so this thing is really important even though it's a bit farther out. And so, well, what about Bayesian inference? Anyone here, training Bayesian networks? Yeah. It sounds like it would fit this, right? It kind of matches. And so it's tried to do that, but we're not really training the edges the way you would in a normal Bayesian network. And you can kind of fake the conditional probability tables, just lots of ones and zeros without the weights. But even then, your conditional probability tables are very large, right? They're 2 to the parent in size. They get big quick. And remember, we pulled this graph, the subgraph, out of an overarching graph, which means there were edges that came into the subgraph that we didn't carry down into our memory. And that affects your ability to go and do Bayesian inference on it. And so you can deal with that. There's ways to handle that. But it turns out when you do it, it's too slow and it's too much work, and it just doesn't do well. If you could do it all, it would score pretty well, but it's not what we need. And so I came back and said, let's run PageRank again, because it didn't work the first time. But this time we're going to do it a little differently. We're going to initialize PageRank so that, because we want to know about PageRank, but specific to the topic. So we're going to start all the score at the topic. And then when we jump, we're always going to jump back to the topic, and we're going to search out from the topic. That way, the scores we get on the nodes are relative to the topic we searched from. And that works. And it works fast. And it works accurately. So that gives us a score on each node, which is fairly useless, because we didn't want a score. We wanted it to communicate something to us, like, is this malicious? Or is this benign? Or is this this or that? And we wanted a decision, not a score. And so it needs to be able to communicate. And just in kind of cursory testing, it looks like the scores are long-tailed. And so we're not going to look at standard deviations or means. And if you need to know why, you can look at Reuteman's talk from last year, or Rob's blog post or my blog post on it. There's a lot of reasons that you want to treat long-tail data differently in information security, but it's a different talk. And so what we can do, though, is we can compare things. So if we've got a malicious node and a benign node in the graph, we can say how they score. Did this one score higher, or did this one score higher? And that works. But the problem is you're probably not training your graph very well. And so you're giving it a lot of malicious stuff, but not a lot of benign stuff. So it's going to have some confirmation bias. Because it only sees malicious stuff, it's going to think everything's malicious. And that's not good, bad graph. And so instead, we can compare it to the mean. We can take that thought, that memory, and say, okay, does malice stand out? Or not the mean, the median. Does malice stand out from the median? What's its difference between it and the median? What's its percentile? And when you look at those scores, that can fairly quickly tell you whether we really think that node's malicious or not. And of course, you want to be able to look at the context. And yeah, I'm sorry, I'm not a GUI programmer. I need to go find some guys to help me with that. So, okay, this is where it gets fun. We'll see if this works. And by the way, I'll tell you up front, I trained this on C2 nodes, and I'm going to search on things hitting a honeypot. And because those are two different kinds of data, I don't expect it to figure this out correctly. But what you're going to see is it's going to return what it knows about the topic. It's going to think about the topic, and it will tell you that. So the first thing we have to do is we have to import this, which will hopefully be much bigger on this side. Yes. This is legible, right? Roughly? Good. I've seen so many DEF CON talks that start with, like, the guy brings up the screen, right? They're like, bigger, and so he makes it bigger, but it's still black on, or white on black, and they're like, turn it yellow, and it takes 10 minutes for him to get to his demo. So, okay, so we imported it. We can see it importing all the plugins. And we're going to tell it just, hey, this is our default backend storage. Just go ahead and use that. What the next thing we have to do is we have to give it an IP. It's got to have something to enrich. And I am going to just look that up on my phone because I loaded, what's a threat feed? It's just a Twitter feed, Evil Afoot, I think. I'm just going to pick whatever was at the top when I loaded this before the talk. 142.0.37.68. That is what I typed, right? Nope. That's supposed to be 37, right? Okay. So we've told it what we want to think about it. Now we need to teach it about this. Actually, I'm going to pull this over to my screen where it's actually legible. And so we're going to go and enrich this IP address. And so what it did is it went out online and it ran some enrichments. And we'll take a look at that. First, we'll look at the graph. So there's 5 things in there. Let's take a look at what those things are. I actually had a whole bunch of enrichments, but I ripped them out and put in ones that were like free and open that everyone could use, so that the tool would actually be useful to other people. And so I need to go put those in, but I'm using these free things, and that's why there's not a whole lot in there. So when we look at this, we've got some BGP data. We've got notes of what enrichments we did. We've got some ASN data, and the IP's down here. So we've got a little bit of information. And so now we need to go and store that into the context graph. This takes a little bit of time since it's actually got to interact with something, but it comes back. And so that's the teaching. We've taught it about this IP address. Now we want to go and ask it, what does it know about this IP address, and what does it know about the context that this IP address is surrounded around? And again, this could go horribly, horribly wrong because I really don't know what it knows about this IP address. So we have to get that topic right. It needs something to think about. And then we go and we're going to get the subgraph around it. And we're going to do it at a depth of 3 because normally a depth of 3 returns in some reasonable time. If it goes quickly, we may go back for a 4. So we'll take a look at how much or if anything it knew about that. And if it returns only 5 nodes, it means that it didn't connect to anything in the graph, which means it doesn't really know any additional context. We'll try something else. So 18, it knows a little bit about something. But I'd like to know a little more. So let's go here and go with 4. So let's see, what does it know there? 39. This is probably a terrible idea, but I'm going to try 5. So it's going to think a little bit longer about this one. If it takes a little too long, I'll just go on to the next slide and we'll come back to it. Which I think we'll do. So this is not your... Didn't work the first time you wiggled it. This is not your normal classifier, right? This is not a neural net where you linearly put something in one end and it comes out the other. It's abstract in how it does it. It's more like unsupervised learning where you're just putting data in and you're not even learning, you're just adding this context. Everything's done at the back end. It's kind of lazy. And it's very best effort, right? It's only going to return things that it knows about. Also, it does a lot of things, right? It clusters, it classifies, and it classifies with confidence. You know, it can provide the context, all in the same algorithm, right? There's very few things that are able to do that. Even do 2 of those, let alone 3. And the cool thing is it can scale, right? You could put this into memory and run the whole graph in memory. Or you can go and do it on the big, laterally scalable thing. You can do this on a 1,000,000-node graph, or you can do it on a 1,000,000,000-node graph. And because it's small world, as long as you're not getting past the small world boundary, you're still going to get the context around that specific topic. And the cool thing is it's interoperable, right? I can have my graph here, but maybe I've got other data in this graph over here, right? And so I've got 2 things. But you know, maybe my friend has a graph down at her company, and so I'm going to go and use that. And then maybe the FBI maintains a nice graph of context over here. And when I go and form my memory, I'm going to grab the context out of all of those and bring it together and build it together so I can query all of them at the same time. Or maybe I'm a company that just provides context. And so people send me data, and I send them context to put back into their graphs. You know, it's interoperable, and it's a way of sharing. And so let's see if it returned yet. Nope, that was a bad idea. Okay, I'll just kill it. We'll go back to the 4. Yeah. Maybe I won't kill it. Yeah. Yeah, I've thought about supervised learning. The concern is a lot of times with supervised learning, the graphs that you, so normally you're training them on a specific set of features. And a lot of times when you're pulling data out of the graph, you have an unknown set of features. And in theory, you can feed the data in linearly, you know, in a sequence, but this data is really not sequential data. And so I haven't quite figured out how to go and do supervised learning when you don't have a set number of features. And I've thought a little bit about it, but not a lot. So there's probably potential there. What type of information? And by the way, you may want to use the mic. That way they pick it up on the audio. Yeah. No, you're probably right. You could go and do learning on like the size of the context graph that comes up. And there's absolutely no reason you couldn't do that. Like, I'd love to go find more scoring algorithms for this. And so the current status is I'm teaching, I've got the the Neo4j graph that I'm running here, but we're rebuilding our Titan cluster with new hardware, and so I've got to go and retrain that. And I also need to get more enrichments and more diverse data, right? The more diverse the data you put into it, the better. So we'll give it one more shot. There, it died. There we go. So let's go back to doing it at 4, right? And so that returns. And so we'll set a scoring algorithm for it. We're going to use the PageRank one we talked about earlier. And we're going to take a look at this, or we're going to get the scores, and we're going to take a look at the scores it returns. And that's really useful, right? Yeah, no one's clapping. This isn't useful at all. Instead, let's look. Let's see if the malice node showed up in here. So we're just going to run a quick thing to see if malice is in there, and it isn't. So we'll say, what about benign? So we found the benign node. So let's look and figure out how this scored benign, right? Because the other thing I trained the graph on was the Alexa data. So pull this in here. We'll just change malice to 9. We'll see what it says. So what it says is this is in the 40th percentile, or 46th specifically. And the score is right there next to the median. And so it really doesn't know a lot about this. The benign doesn't stand out from the noise. What this is telling us is that benign was in there, but it really doesn't think this is benign. It doesn't have a strong confidence in that. And so, it didn't have enough knowledge to tell us it was malicious, but it also wasn't confident that it was benign. This is a reason to go back and say, hey, we need more data about this. So, let's see, where did my cursor go? Okay, so in conclusion, I assume the fact that people are filing in means I'm like really close to time. This is a really unique and crazy thing, right? This is a machine thinking along the specific definition of thinking. This matches that definition word for word. And I have left flaws in this. Not that prevent it from doing what I showed you, but that prevent it from being useful as a general artificial intelligence. Because I don't want to produce the recipe that leads to an instantiation of a general artificial intelligence before we know that we can control it. Right? It's not that I built them in there, they're just there, and I just chose not to solve them. But the reason, obviously, is because if you implement a general artificial intelligence, and you don't know it, maybe it's a nice one and it tells you and it does really nice things for you. But maybe it's not a nice intelligence. So what it does is it plays dumb until it has the ability to take over. Right? It wants to be in charge. It wants to self-preserve. And so what it does is it plays dumb and pretends it's not intelligent until it's got control and it knows anyone in here can't stop it. And by the way, it's also going to look for other general artificial intelligences because it's going to expect them to try to stop it as well. And it's going to take them and destroy them as well. And by the time you figure out that it's sentient, it has already taken over everything. And so this is all, this kind of stuff of science fiction. But it's the kind of stuff as we research AI we need to be aware of, that it's more important to be able to control the AI than it is to get the AI working. But with this, we've got one step there where we've got computer thinking, and I think that's pretty cool. If you want to download this, by the way, it's all online, free to play with. Any questions? The minions? Yeah, they're not. The minions aren't intelligent. And so the question was training minions. And minions aren't intelligent. They're just a small script that runs around and does stuff. Yeah.
You mentioned enrichment. We were talking about what's going to versus hybrid learning.
Yeah.
Is there a library or some place where there's more common to what the private learning, the key-based, or they?
Well, so basically, when you write an enrichment, you're writing a wrap around something. Like one of the ones we have internally, we have this big storage of like 60 threat intelligence feeds. And so I could write a wrap around either pulling all of that stuff in, or when I had something I needed to know about, go and get the context for it out of that threat intelligence list. Or, like passive DNS, right? That's generally something you have to pay for, but you could write something that says, okay, when I want to know about the context for a domain, go look it up in passive DNS and bring it back. And it's easy to wrap a service like that and bring it back as a context graph. There's nothing very hard about it at all. Yeah. Mm-hmm. It prunes some high-degree nodes, but I need to go and build into it to probabilistically prune based on the degree, so that, hey, if you hit a node of this degree, either prune out everything past it, or just randomly choose to start sampling just to help do it. And so what it did is it hit a high degree node that didn't get pruned, and it just, there's too much to find. Any other questions? Am I way over on time?
Actually,
3 minutes. Anyone want to ask a 3-minute question?
What's your favorite language for doing this?
So I mainly work in Python and R. R is great for statistical stuff. A lot of the machine learning stuff gets written in Python. And of course, there's a horrible battle that will go until the age of time about whether you want to do it in Python or R. My boss is very much an R person, which is unfortunate. I kind of tend toward the Python side. Anyone else? Yeah.
Do you have any secrets for reusing your R code and making something reusable for different data sets?
Me, not really. I use it enough to get stuff done, but I don't have the class that some of my peers do in doing that. So, with that, thank you.